from this point on in the course, we kind of change gears here a little bit. Up until now has been, a lot of terminology. It's been our general introduction to organic chemistry. For the rest of the way in this course, what we do will focus on functional groups. And basically, we go one functional group at a time. And as we cover each one of those, we will do things such as nomenclature, properties. Those properties could include things like melting points, boiling points, solubility, acidity, basicity. And then for most functional groups, we'll get into some reactions. But for now, this next section is going to be on what we would call unsaturated hydrocarbons. So this term unsaturated is something that you've probably seen before. You may even have heard it in other contexts. But what we're referring to are carbon-carbon double bonds, triple bonds, and aromatic rings. And each of these can be referred to as unsaturated because they have less than the maximum number of hydrogens for the number of carbons that they contain. And the place we've probably seen this is in fats. We hear the term unsaturated fat pretty often. What does that term actually mean, unsaturated fat? Well, unsaturated fat is literally one that's somewhere in its chain. So most fatty acids are generally a carboxylic acid group with a long carbon chain, 12, 14, 18, 20 or more carbons. A saturated fat, or a saturated fatty acid, has the maximum number of hydrogens and might just look very simply like this. But unsaturated is missing a couple of those hydrogens somewhere in it. Has a double bond. So it's short two hydrogens. And so that's the difference between a saturated and unsaturated fatty acid, is whether they have a double bond, or in some cases more than one double bond. Now, of the three functional groups we mentioned to start this section, alkenes, alkynes, and aromatics, two of them are much more important in the context for this course. Alkenes are something we definitely see naturally. We see them biologically. We see them in a lot of contexts, as we've already seen based on the fatty acids. Aromatics are everywhere. There's not much you can do to avoid aromatic compounds. The third one, alkynes, are a lot less common in nature. And so while we will discuss them, we won't discuss them to the extent of the other two functional groups. But we still include them here because, as we'll see, a lot of the things that alkenes can do, alkynes also do. The common difference, though, is that in many cases, alkynes can do those reactions twice, whereas alkenes can only do them once. But we'll get to that later on in this chapter. So the first thing we want to say about alkenes is just talk a little bit about their geometry. Because unlike alkanes, or any carbon with 4 single bonds, the carbon of an alkene has geometry of trigonal planar, bond angles of 120 degrees. So we've got a different shape than we do for other molecules. But in addition to that, alkenes have another property that we don't see in alkanes. And that's this bond cannot be rotated about. So most single bonds that we deal with have free rotation. And that has various consequences within chemistry. But alkenes don't. And so one of the things that leads to is if we have a molecule such as this one, this hydrogen is very close in space to this methyl group. But this hydrogen is on the complete opposite side of the molecule, and they're locked into those positions. And so as we'll see later on, that's going to have some consequences as well when it comes to both nomenclature as well as reactivity. But before we get that far, we can say that a carbon-carbon double bond has 4 total electrons, 2 from each carbon, and it's also stronger as well as shorter than a carbon-carbon single bond. Typically, the more electrons you add to 2 atoms sharing, the stronger the bond gets, and if the bond gets stronger, the bond almost always gets shorter as well. Now, alkenes are also much more reactive than alkanes. So we talked about alkanes earlier in this course. And what was our main conclusion there? Well, we said alkanes are boring. They don't do much. Alkenes actually do quite a bit and play a role in some biological processes as well as many other things. And without getting too far into the sort of the orbital issue, when we have a double bond, or let's start with a single bond. When we have a single bond, this is known as a sigma bond. When we have a double bond, the first bond of that is known as a sigma bond. The second bond is known as a pi bond. And the location of the electrons in the pi bond is different than the location of the electrons in the sigma bond. Let's picture that in another way. So the sigma bond is directly between the atoms. And so those electrons are more blocked, more shielded than the rest of the molecule, than others. But the pi electrons are up here and down here. And so if you think of the rest of our molecule, our trigonal planar geometry, like this, this is basically a plane going into the board, whereas the pi electrons are above and below that plane. And so again, without getting too deeply into this, what we want to say here is that these pi electrons are more accessible, they're more exposed, and they end up being much easier to interact with other compounds.